Hi, I'm Patrick Reagan. Welcome to the TCP/IP Part 19 Troubleshooting IP Networks Part 2. During this video, we will continue our discussion on troubleshooting IP networks with a focus on more advanced commands such as ARP, netstat, protocol analyzers, speed test, APIPA addresses, and IP conflicts. As with most of my videos, there are practice questions at the end of the video. If you like this video, click the like button. And if you have not already, subscribe to the Pat Has Your Back channel. Address Resolution Protocol, or ARP, is a fundamental network protocol used to map an IP version 4 address, layer 3, to a MAC address, layer 2, on a local area network. The ARP command is a valuable tool in network troubleshooting, especially when diagnosing IP to MAC address resolution issues on local network. It's mainly used to view or manipulate the ARP cache, which stores mappings between IP addresses and MAC addresses. It can be used to help identify IP conflicts or duplication, determine if MAC addresses are being resolved properly on OSI model layer 2 devices, ARP spoofing and poisoning, and diagnosing of broadcast domain issues. To display the current ARP cache table in Windows and to see if an IP address has been resolved to MAC address, you would execute ARP-A. To delete an entry from the ARP cache in Windows, you would use the ARP-S option. To view the ARP table in Linux and Mac OS, you would execute IP-NA. If no MAC appears after pinging, ARP resolution may be failing, which points to an incorrect IP, devices down, or VLAN misconfiguration. If two MAC addresses appear for the same IP at different times, there is likely an IP conflict. Here is show running the ARP-A command in Windows. An ARP table on the switch is primarily used to map IP addresses to MAC addresses within its local network, enabling efficient communication between devices. It helps the switch forward traffic to the correct destination by translating the logical IP address into the physical MAC address. Administrators might view the ARP table on switches to troubleshoot network connectivity, identify potential issues like duplicate IP addresses or incorrect MAC address assignments, and enhance network security by monitoring connected devices. The exact command will vary depending on the switch vendor and model, but common commands include show ARP for Cisco devices or display ARP for some HPE and Aruba devices. Some switches may also have a web-based interface where you can find the ARP table information under IP or network configuration settings. The netstat command is a powerful diagnostic tool used to troubleshoot network issues by displaying active network connections, routing tables, listening ports, and interface statistics. It can show if you have an active connection, verify services bound to an expected port, identify unknown or suspicious IPs or processes, confirm if connections are established, and show raw IP addresses if name resolution fails. This page shows the various available netstat options. Netstat-A shows all active connections and listening ports, while netstat-N shows IP addresses and ports. Netstat-B in Windows shows the executable program or process using each connection. Netstat-R shows the routing table, and netstat-I and -E show the interface statistics, including errors. Netstat-S shows the protocol level stats. Here, you can see the netstat-A, netstat-E, and netstat-S commands. Windows Resource Monitor is a built-in system diagnostic tool in Windows that provides real-time data on how system resources, CPU, memory, disk, and network are being used by applications and services. It's especially useful for performance troubleshooting, identifying resource bottlenecks, in diagnosing unresponsive applications or network issues. The Network tab shows usage by process, TCP connection, and listening ports. Here, you can see the Resource Monitor Network tab that shows TCP connections, listening ports, and network activity. A protocol analyzer, also known as a packet sniffer or network analyzer, is a tool used to capture, decode, and analyze network traffic at the packet level. It's essential for troubleshooting network issues, monitoring performance, detecting security threats, and debugging application protocols. A protocol analyzer captures packets from a network interface, decodes protocols at each OSI layer, displays data in human-readable form, and applies filters to isolate specific traffic. It also analyzes communication patterns, errors, retransmissions, handshake failures, and so forth. To make effective use of protocol analyzers such as Wireshark or TCPDump, you need a combination of technical knowledge, practical skills, and contextual awareness of your network environment. You'll need to have an understanding of common protocol interactions such as handshakes, IP addressing and subnetting, ports and protocols, MAC addresses, and ARP. You need to know what normal traffic looks like in your environment so you can spot anomalies such as missing acknowledgements, high retransmission, and ARP floods. It can be used to determine if packets are reaching or leaving a system, capture and analyze DNS queries and responses, inspect TCP handshakes and retransmissions, verify inbound and outbound connections are attempted and accepted, detect retransmissions, TCP resets, or malformed packets, and spot unauthorized connections, ARP spoofing, and suspicious payloads. Here, we're looking at Wireshark Protocol Analyzer that is showing a packet including the Layer 2, Layer 3, Layer 4, and upper layers of the packet. Here is a closer look. This particular packet is using Ethernet 2 with the source and destination MAC address, which is Layer 2. It is using Internet Protocol version 4 with its source and destination IP addresses, which is Layer 3. For Layer 4, it is using TCP, specifically source port 443, which is used by HTTPS, specifically TLS version 1.3 with an encrypted payload. For example, to determine why a user is not getting a DHCP address, you can use the protocol analyzer like Wireshark or TCPDump to inspect the DHCP exchange between the client and the DHCP server. The DHCP DORA processes 4 steps that include DHCP Discover, where the client's broadcast out is any DHCP server out there. The server responds with the DHCP offer, here's an IP address you can use. The DHCP request is when the client says, I want to use this IP address. And DHCP acknowledgement, the server says, you're now assigned this IP address. You should know that DHCP uses UDP port 67 for the server and port 68 for the client. You can use this to filter out so that you can focus on the DHCP conversation between the client and the server. If no Discover broadcast packet is sent, the NIC is disabled, cable is unplugged, or you have a bad switch port. If the Discover broadcast packet is sent, but no offer is received, there's no DHCP server on the subnet, the DHCP server is down, or you have a VLAN misconfigured. If the offer is sent, but no request is sent, the client is not responding to the offer, which means there's an issue with the client OS, DHCP configuration bug, or firewall. If the request is sent but no acknowledgement is received, the server may refuse the lease because the scope is exhausted, server policy, or conflict detected. The DORA handshake is completed, an IP address is not assigned to the client, it is a client-side issue. As you can see, you have to understand the expected process so that when looking at the interactions, you can determine where the failure is starting. If you want to learn about using protocol analyzers, check out the content by Laura Chappell, who has written books, created videos, and conducts classes. You can start with her Chapel University videos shown on the screen. Wireshark is free and open source network protocol analyzer used for capturing and inspecting network traffic, and is widely recognized as the most popular and commonly used protocol analyzer. It allows users to see what's happening on the network at a microscopic level, making it a valuable tool for troubleshooting, security analysis, and protocol development. It has a user-friendly GUI for easy navigation and analysis, and runs on various operating systems like Windows, Mac OS, and Linux. Wireshark can capture network data packets from various interfaces like Ethernet, Wi-Fi, and Bluetooth. It analyzes traffic by dissecting and displaying the captured data, making it readable and understandable by humans. It filters packets based on various criteria, allowing you to focus on specific traffic of interest, including source and target IP addresses and ports. It can decode hundreds of protocols, providing detailed information about each packet and its content. It can capture live traffic or analyze captured packet data from files. The TCPDump command is a powerful packet capture and network analysis tool available on Unix and Linux systems. It's used for troubleshooting network issues by capturing and inspecting network traffic at a very granular level. To capture all traffic on the Ethernet interface, you use sudo TCPDump-I each 0. Use Control-C to stop. To capture traffic on a specific port, use sudo tcdump-I each 0 host and the IP address. To capture traffic on a specific port, use sudo tcpdump-I each 0 port and the port number. To read from a saved capture, use tcpdump-R and then the name of the PCAP file. A PCAP file, short for packet capture, is a file format used to store network traffic captured using tools like Wireshark or TCPDump, which contain raw data packets providing a detailed record of the network communications for analysis and troubleshooting. You can create a PCAP file with TCDump and then use Wireshark to analyze the packet with a graphical interface. A speed test in networking measures the performance of an internet or network connection. It evaluates key metrics such as download speed, upload speed, latency, and sometimes jitter and packet loss. These metrics help assess the quality and capacity of your connection, useful for troubleshooting, verifying SP performance, and planning bandwidth usage. The table shows you some expected home and office expected speed ranges. And here's a table showing speed performance in an enterprise environment. When looking at your download and upload speeds, you need to look at what is expected and compare that to its expected load, determine if the network is operating at its full or expected capacity. And some more expected performance for VoIP and video calls, cloud file sharing, and remote desktop connections. Some of the common command line diagnostic speeds include speedtest-CLI, mperf3, netperf, and netcp. There are many internet speed test sites that can be used to test your internet speed. Speed Test by Oakley is the most popular that shows server location and share results. There's also Google Internet Speed Test and Fast.com, which is the Internet Speed Test by Netflix that is good for streaming and testing. A good download speed is at least 100 megabits per second, and a good upload speed is at least 10 megabits per second. The 100 megabits per second, you can watch Netflix or YouTube, attend Zoom meetings, and play most online games on several devices at the same time. If a computer is configured to receive an IP address from a DHCP server and one does not respond, the computer will use the automatic private IP addressing, or APIPA, which starts with 169.254 and a subnet mask of 255.255.0.0. If this happens, make sure you're connected to the network and the DHCP server or device is running. The DHCP server is on a different subnet than the clients it is servicing. Make sure the DHCP relay agent or IP helper is running and that they are configured to point to the DHCP server. APIPA addresses can also be caused by address pool exhaustion if you run out of addresses for a scope. You can use IP address management or IPAM to help monitor and report on IP address shortages. A temporary fix could be to lower the lease time. It could also be caused by a duplicate or conflict IP address. An IP conflict occurs when two or more devices on the same network are assigned the same IP address. Since each IP address in a network must be unique, a conflict prevents one or both devices from communicating properly. IP conflicts are caused by static IP overlap with DHCP, where a device is manually set to an IP address that's also in a DHCP pool. Duplicate static configuration, where two devices are manually configured with the same IP. Clone VMs or images, where virtual machines or system images are deployed without changing the IP settings. Multiple DHCP servers, where more than one DHCP server hands out overlapping IP ranges. And VPN subnet overlap, where a remote client or site shares the same subnet range as the local network. Common symptoms of an IP conflict include IP address conflict warnings, where most operating systems show a system notification or event log alert. No network internet access, where the device may lose LAN or internet connectivity. Intermittent connectivity, where connection may randomly work and fail as ARP tables flip between devices. Packet loss or high latency, especially when communicating with or through the conflicted IP. Services unreachable, where web servers, remote desktop, and file shares may not be accessible. Wrong or delayed DNS responses, as the DNS queries gets routed to the wrong device IP. Flapping ARP entries, where a switch or router shows MAC addresses constantly changing for a single IP. DHCP errors and logs, where the DHCP server may detect conflicting leases or reject requests. Client fails to obtain IP, where it falls back to the IPAPA addresses if DHCP fails due to conflict. And devices visibly under wrong MAC or IP, where the device appears under the wrong address in monitoring tools. To troubleshoot duplicate IP addresses, check your IP addressing to see a misconfiguration. Ping an IP address before static addressing to see if it's already being used. Ping the IP address and check your ARP table and find the MAC address in your switch MAC table. Use a packet analyzer to capture the DHCP process to see what DHCP servers are responding. Address pool exhaustion in DHCP occurs when the DHCP server has no more IP addresses available in its configured pool to lease to new clients. This means that the devices requesting an IP address will not receive one, resulting in network connectivity failure. This is caused by too small of a scope or pool, where the defined IP range or scope doesn't have enough addresses to accommodate all devices. IP address hoarding, where devices hold on to leases longer than necessary, especially with long lease durations. Stale leases, where IPs are still marked as in use even though the clients are no longer active. Unauthorized rogue devices, where devices are not meant to be on the network, consumes IP addresses. Storage due to subnetting or misconfigured or overly segmented subnets reduce the number of usable addresses. Improper reservations, where you have too many IPs, are reserved for specific devices, reducing the available dynamic pool. And the HTTP denial of service attack, where malicious clients repeatedly request IPs until the pool is exhausted. Question: you're investigating why users cannot reach a Linux web server with a browser but can ping the server IP. The server is online, the web server process is running, and the link to the switch is up. Which of the following commands should the administrator run on the server first? Answer: netstat. You can use the netstat command to see if the web server is listening on the correct port. Question: you're troubleshooting an application issue after a firewall change. The administrator has confirmed that the port and protocol are accessible to the user, but the application is still having issues. Which of the following tools allows you to look at traffic on the application layer of the OSI model? Answer: TCPDump. Question: a virtual machine has the following configuration shown on the screen. The virtual machine can reach co-located systems but cannot reach external addresses on the internet. Which of the following is most likely the cause? Answer: the DHCP server is offline. Question: what command would you use to display the ARP cache table in Windows? Answer: ARP-A. Question: what command would you use to show all active connections and listening ports on a Windows server? Answer: netstat-A. Question: what command would you use to show inbound interface statistics? Answer: netstat-I. For more information, refer to these sites. In summary, Address Resolution Protocol, or ARP, is a fundamental network protocol used to map an IP address, layer 3, to a MAC address, layer 2, on a local area network. The netstat command is a powerful diagnostic tool used to troubleshoot network issues by displaying active network connections, routing tables, listening ports, and interface statistics. A protocol analyzer, also known as a packet sniffer or network analyzer, is a tool used to capture, decode, and analyze network traffic at the packet level. It's essential for troubleshooting network issues, monitoring performance, detecting security threats, and debugging application protocols. To make effective use of protocol analyzers such as Wireshark or TCPDump, you need a combination of technical knowledge, practical skills, and contextual awareness of your network environment. A speed test in networking measures the performance of an internet or network connection. It evaluates key metrics such as download speed, upload speed, latency or ping, and sometimes jitter and packet loss. If a computer is configured to receive an IP address from a DHCP server and one does not respond, the computer will use the automatic private IP addressing, or IPAPA, which generates an IP address in the form of 169.254.something.something and the subnet mask of 255.255.0.0. An IP conflict occurs when two or more devices on the same network are assigned the same IP address. Since each IP address in the network must be unique, a conflict prevents one or both devices from communicating properly. Thank you for watching this video. The next series will be network switches. If you like this video, click the like button, and if you have not already, subscribe to the Pat Has Your Back channel. Thank you.